Okay, so decided to go ahead and just give you a little video instead of using class time for the introduction to vector applications today, just so you would have more time for the quiz. All right, so this is the Google Slides that is in today's folder, so you can go back and look at it. So the reason it's called plane, trains, and automobiles is because those all have speed in a certain direction, which is the main definition of vector. So velocity is a vector quantity that refers to the rate at which an object changes its position. If you go back to our vector notes from Tuesday, we talk about velocity at the beginning of the notes. When evaluating the velocity of an object, you must keep track of direction. Velocity has two elements. It has speed and it has direction. So it's not enough to say that an object has a velocity of 55 miles per hour. That would be its speed. One must include the direction information in order to fully describe the velocity of an object. So instead of saying 55 miles per hour, you would say its velocity is 55 miles per hour east. Speed is just a scalar quantity, so it doesn't keep track of direction, whereas velocity is a vector quantity and is direction aware. So an airplane moving towards the west with a speed of 300 miles per hour has a velocity of 300 miles per hour west. So as we've discussed before, when we're doing vector operations, to find the component form of a velocity vector, you need its magnitude and you need its direction angle. And the component form of that vector would be the magnitude, cosine direction angle, magnitude sine direction angle. So speed is going to be our magnitude. So when we talk about magnitude, we can call it the length, the speed, magnitude. There's a lot of different words we can use, and we're still talking about magnitude. So when we talk about applications, normally your magnitude is going to be your speed. And then you have your direction angle, because again, velocity includes the direction, not just the speed. So you have this component form of your vector. Find the component form of the velocity vector that represents an airplane descending west at a speed of 100 miles per hour at an angle of 30 degrees below horizontal. So it's descending west. So the descending, so it is west, but it is at an angle of 30 degrees below that western direction. So remember that for our angles, we go back to our unit circle and we always start at the positive x-axis and then we rotate counterclockwise. So if it's 30 degrees beyond our west direction, then that would be your 180 to get you to the west direction, plus that additional 30 would give you a direction angle of 210. So if the speed is 100 miles per hour and your direction angle is 210, then your velocity vector would be 100 cosine 210, 100 sine 210. You would just use your calculator, although this is a special angle. And you can see right here that you have your velocity vector in component form. So again, your magnitude is the speed, your direction would be that 180 would get you to west, plus 30 for the direction angle makes 210. And that's where your direction angle goes, and you do that in the calculator. Okay, so if you had a speed of a plane is 200 miles per hour and the direction angle is 225 degrees, find the component form of the vector. So it would just be 200 cosine 225, 200 sine 225. You would use your calculator, and there would be your component form of your velocity vector. Using vectors to find speed and direction. So a plane's course is in a specific direction. That's one vector. Then you're going to have some wind that is going to affect the plane's course. So the wind is another vector. The resultant is called the ground speed. So the resultant is basically the addition of the plane's course that the pilot sets the settings on the plane to go. And then when you factor in the wind and its effect, that's where you get your resultant. Okay, so you will use bearings And so I've included some more information in today's folder to go into more detail about bearings. But basically, when you talk about planes and ships especially, those use more navigational directions. So we go to the compass when we have north, south, east, and west. A bearing is from the north and goes clockwise. So you always, if you see anything with a bearing, then you want to figure it out based on starting at the north direction and rotating whatever the bearing is towards the clockwise direction, so towards the east. But when we do our math calculations, we need to use the math version of that angle, and our math angles start in the east direction and move counterclockwise. So for problems that mention bearing, you will have to adjust your bearing angle to our math angle based on our unit circle. So if it was a bearing and it says north, that would be 0 degrees because that's where we start. East would be then a rotation of 90 degrees, south would be 180 degrees, west would be 207 degrees. But if I said west and I want to use my math angle, that would start in the east direction and rotate counterclockwise. And so a bearing of west would be 270, but our math angle would actually be 180. So here's your first example. An airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. The plane reaches a certain point where it encounters a wind that has a velocity of 70 miles per hour in the direction of, this is 45 degrees east of north. That means you start north and you rotate 45 degrees towards the east. What are the resultant speed and direction of the plane? So there's several parts to this. You need a plane vector, you need a wind vector. For the resultant, you need to add the plane vector to the wind vector. And when you get your resultant vector, you will then find its magnitude for the speed and use your tangent formula to find the direction. Okay, so the airplane vector, it said a bearing of 330. So remember, that means we start in the north direction, we rotate clockwise to get to 330. Okay, it's 30 degrees shy of returning back to our north direction because that would be a first full circle. But when we calculate, we need to go back and start at the positive x-axis and rotate counterclockwise. So then that 330 degree bearing would actually be 90 degrees plus this 30 degrees. So we're actually going to use 120 degrees for our airplane vector. You definitely want to sketch these out in a coordinate plane so that you can figure out what the given angle is and what the math angle is that you need to use. So for the velocity vector for the plane, we are going to need the speed, which was given at 500 miles per hour, and we need, again, the direction angle. It was given as a bearing, and then we have to convert that to our math angle. So a bearing of 330 is actually a direction angle of 120 degrees because we need to go back and start at the positive x-axis and rotate in a counterclockwise direction till we hit that same place for our vector. So we would use 500 cosine 120, 500 sine 120, use our calculator, and we get our velocity vector for the plane. Then we have to come up with the velocity vector for the wind. So the wind is a 45 degree angle. It is east of north. So again, you would start in a north direction and then rotate 45 degrees towards the east. And then you would figure out what that is with a math angle. The speed was 70 miles per hour. So for 45 degrees east of north would actually also be 45 degrees because since the quadrant's 90 degrees, if I go 45 degrees towards the positive x-axis from the positive y-axis, that would still give me 45 degrees starting at the positive x-axis and rotating towards the y-axis. And then use your calculator and you get your velocity vector for the wind. The resultant would be the sum of the plane vector and the wind vector. So I know you probably can't see that because that banner is covering it. So the magnitude of the resultant. So we have, this was our vector that we got when we added our plane vector to our wind vector. The speed is going to be the magnitude. So you take this vector and you do the square root of the first number squared plus the second number squared, and that gives you the resulting speed of the plane, considering the settings on the plane and the factoring in the wind. So it actually made it a little faster. Then we need to find the actual direction of the plane when the wind is factored in. So we do the inverse tangent of the second number divided by the first component. Make sure it's going in the same quadrant. So this resultant vector is in the second quadrant because you go left and up. And so our direction angle should also be in the second quadrant. So remember that when you do an inverse tangent, it's going to give you either a first quadrant result or a fourth quadrant result, and you're going to have to add either 180 or 360 to change it to a positive direction angle in the correct quadrant. So when we do our inverse tangent, we get a negative angle on the fourth quadrant, but this resultant vector is in the second quadrant, so we add 180 to get the correct direction angle. And so the math angle is 112.565. So if you figure out that's from the positive x-axis rotating counterclockwise, then you can adjust that for a bearing. And there's several ways that you can write that. It doesn't have to be stated 22.565 west of north. You could also adjust it back to if you started at north and rotated all the way clockwise to get to that same angle and call it just a plane bearing. So here's another example. An airplane is flying with a bearing of 148 degrees with an airspeed of 175 kilometers per hour. Because of the wind, its ground speed is 800 kilometers per hour. Bearing is 140. Find the direction and speed of the wind. So before we were given a plane vector and a wind vector, and we had to add to get the resultant vector. Here we are given the plane vector, and then the ground speed is the resultant vector, and we have to find the wind. So if plane plus wind equals resultant, then resultant minus plane would give us the wind. So we're given the plane vector, which is that red vector. It has the speed of 875, that's kilometers per hour, so that's why it's a little higher. It gave us a bearing of 148. So remember again, that's starting north and rotating clockwise. And then we can adjust that back to what if we started here on the positive x-axis, and you could either rotate, you can use a negative angle rotating clockwise, or you can do a positive angle rotating counterclockwise. And then the blue vector is the resultant vector. So the plane vector, remember again, 148 is the bearing, it's not the direction angle. And so a bearing of 148 is the same if you started at the positive x-axis and rotated counterclockwise would be the same as 302 degrees. You can figure out, here's 90 degrees, so this would be an extra 58 degrees, so 302 is just the full circle minus that extra 58 degrees. So you get your plane vector, then we work on the resultant vector. So it said that the bearing was 140. So again, from north, that's 90 degrees clockwise plus an extra 50 degrees. So we need to figure out the direction angle. And if we start here at the positive x-axis and rotate counterclockwise, it would be a full circle minus this little 50 degrees, and the direction angle would be 310. And then you get your resultant vector. So again, the plane plus the wind is the resultant, so that means that the resultant minus the plane is equal to the wind. So if we do that on math, we get a resultant vector or a wind vector right here, and then we want to find the wind speed. So we take the magnitude, which is just the square root of the first component plus the second component, each of those numbers squared and then added. Take the square root, you get the wind speed at 138.74 kilometers per hour. And the direction would be that tangent formula. And so when you find the tangent, you get the 68.632 from your calculator. The wind vector is in the first quadrant, so this reference angle is in the correct quadrant. We just have to adjust that as a bearing. So this angle is starting at the positive x-axis and rotating counterclockwise. We need to adjust that. If you were to go back and start at the positive y-axis and rotate towards the positive x-axis, it would really just be 28.368. You can say it east of north, or you can just say bearing. In this case, it would be the same thing. Okay, that's it. So you have some problems that you're going to do for practice. I'm going to share that in your folder. Basically, if it runs through the problems, you're going to have the first one where you are just doing what we did at the beginning of the presentation, where you're just creating a vector given the force, which is the same as the speed, and then the angle. And so you would just be doing this part where you're just creating a vector and then typing it in your calculator. So just similar to this. For 2, you have 3 forces, so you're going to have 3 vectors. Again, the force in this case would be your magnitude, and then you are given an angle. So far, they haven't mentioned any bearings, so the angle given is the angle that you use. Then when you get into number 3, this is where we start mentioning bearing, and you have to adjust the bearing to an actual direction angle. So you're given the airplane vector, you're given a wind vector, you'll find the velocity vector for each of them and then add to get the resultant. And then you'll go through and find the magnitude and the direction, so similar to what we did here. And the last one, you have an airplane pilot wishes to maintain a true course. That's your resultant. So you're given the ground speed initially, you're given the resultant, you're given the wind, and you'll find the vectors for each of those, and then you'll subtract the resultant minus the wind to find the velocity vector for the plane.